everyone. In this second video of this series cost planning, I'm going to talk about the contingency estimate. I really believe many of us who are working in the construction field are very familiar with the term contingency, which is an allowance for risk and unforeseen items that may be happen during project progresses. However, when it comes to the quantification of contingency estimates, it can be augmentative. For example, if we ask some people who are working in the construction industry but not risk experts, their answers could be varied. They may consider the contingency of a construction project is about 2%, 5%, or even 20%, depends on their own experiences and historical data they have. Regardless of this forecasting contingency, me personally have seen many projects completed but over budget significantly because of variations. Therefore, the risk assessment approach has been developed and widely adopted by the construction industry in quantifying contingency more accurately. So, it's essential to discuss some relevant statistics parameters because, as I have said before, this risk assessment approach relates to many statistics parameters. So, as example, we have tender submission for with the contractor A to E with the respective the tender submission from 20 to 30. And the first important parameters is the mean. Mean average. Average is very straightforward. You total sum all the submission and divide 5 tenderers is equal to 40. And the variance is the difference around the mean. So we can see here 20 minus mean 40, 40 minus mean 40, and square we have 200%. The purpose of the variance is to get rid of the negative amount some feature. And we move to standard deviation. Standard deviation is the square root of variance is equal to 40. The standard deviation gives us the difference between the means of the tender submission. And then when we have the mean, variance, and standard deviation, we can calculate the normal distribution of bell curve by using the Excel function norm.ist, and we have here our normal distribution. Then we use this to make a bar graph in this in here. This we call the bell curve. This step looks like a bell, and we can see the bell curve with has the mean at the center, and to the left they will minus 1 standard deviation, and to the right they will plus 1 standard deviation. And it's very important because when we calculate the contingency, we have to use this type of bell curve. And another very important parameters is the percentile. In here we have percentile B10, B50, B90. It basically is the percentage of a cost will happen. For example, if we say the cost of 10 million is B50, that means 50% the projects will be completed with 10 million, and so on. And for probability range, that means the chance of an event will be happens. So the percentage will be will be from 0% to 100%. And the last one is 3-point estimate, but is equal to best case and most likely and worst case divided 6. For example, when we estimate a construction item, we usually have only one most likely feature. We don't put the best case or worst case. So one of the approach we can use to calculate the contingency estimates at the brief stage, where we don't have many information, just very limited data perspective. So we can apply the formula total estimate is equal to base estimate times 1 plus factor n1 for contingency n1 plus factor nn for the contingency nn. For example, we will estimate contingency for an apartment project at the brief stage. The base estimate is 100 unit total, 100 unit apartment times 550,000 per unit equal to 55 million for the base estimate. And factor M1 the contract, the contingency will be 10% of the total base estimate. And factor N2, factor N3, factor N4. Based on the formula, we will have total estimate including contingency, and most likely is equal to 55 million base estimate times 1 plus 10% plus 2% plus 10% for client plus 5% variation, then equal to 70 million. And the contingency can be calculated straightforward. Is equal to 70 million including contingency divided by estimates. We will have the contingency 15 is 15, not 5. And we will apply the Excel function norm dot inverse with probability. Probability is our B10, B50, B90, as I have explained earlier, and mean is our most likely here, and standard deviations is our contingency at B50, and B10 means the 10% that the project will be completed with budget of 51 million, and B50 means 50% the projects will be completed with 70 million of budgets, and the same for B90. And now I will demonstrate in Excel how to calculate the function norm inverse. We will apply the norm inverse to calculate total amount of contract at B10 is equal to norm inverse here, and B10 we will probability 10% here, and means our total estimates more likely here, and standard deviation is 15 here. Okay, so 10% the contract will be completed within the budget of 51 million, and we do the same for B15, B90. I will copy the formula, but we have changed here norm here and here, but now we change to 50%, 50 and we will fix this cell by click F4, then copy. Now we change this one to 90%. Is 89 million. So, and when the design is available, we should not use our calculation of contingencies based on the previous state estimate, but we apply our first principle, that means the detail of contingencies instead of giving the percentage 10%, 2%, 10%, 20% like we have done previously. Then now we have WBS for the list of risk and contingency that can be happen for our projects. In reality, before calculation the contingency, the risk assessment team will organize meeting with a relevant expert and stakeholder to discuss and identify what are the risks that can be happened for the project. In here, we may accept some risks already discussed, for example, the soil excavation. And BX here is the probability this risk or contingency can be happen is 100%. And for hitting a live electrical, the probabilities can be happen is only 5%, maybe because we only have the SP drawing and it's hard to happen. And the same for others. And then we have the best case, most likely, worst case by estimating as usual. And most likely we can have by estimating based on our drawing or our available informations. But for best case and worst case, we will be based on maybe the normal distribution like bell curve and standard deviation we have discussed previously. And in this column, we will calculate the weighted average on the burst is equal to best case plus 4 times most likely plus worst case divided by 6, and then we have this column. And the B50, that means 50% the projects will be completed within this cost is calculated by B50 is equal to BX is probabilities. It can be happen here times the weight average, because this item is soil excavation, the probability is 100%, so 100% is 1 times with 50 is equal to 50. And we apply the same. For example, hitting a live electrical is 5%, 5% times 20% is around 1. And for B90 is equal to B50 plus 2 standard deviation times BX. We have 70. The exact calculation with the theory of bell curve that I have discussed earlier, and we use this manual calculation because maybe we don't have any software available like S-Risk or Primavera risk analysis. We have no choice but use this manual calculation. And because I have my software Primavera risk analysis available with me, so I will use this to double check the manual calculation. They have used the software Primavera risk analysis to calculate the contingency for the previous projects. First, I will open the software and then click edit file and then click new, and there are two templates appear here, the new plans and symbol cost estimates. For new plans, it will allows us to do the estimates for contingency with risk register, correlation, and resources, many things. Um, but in for the cost planning purpose, we may not have the sufficient information, so we use this simple cost estimate, and we'll hit to this icon and click, double click, and it will have our screen here. I will copy the information here and paste, and then probability, and then deterministic cost. Deterministic cost is our base estimate, or here is more likely. Most likely. We can see here the probability of occurring already put it here, deterministic cost, and mean fixed cost, likely fixed cost, math fixed cost. Is the best case, most likely, and worst case. Because the software already have the probability in here, so when I copy the likely fixed cost here, it will automatically appear the mean fixed cost and max fixed cost based on the risk burst. 70 minimum 75%, likely 100%, and maximum 125%. We can check it by click to risk and duration quick risk is minimum duration, and click cancel. And then when we have the probability here, we can start calculate to run the risk analysis. As you can see here, there is a cost and risk output and gain and grab. Gain and grab is allow us to put the schedule for this contingency, but um, I really believe for the cost planning we may not need to apply the resources and schedule because we don't have sufficient information, so I only use the cost here. And then if we click the resources here, it will automatically apply the fixed cost for us, For example, the units is 50 here. In case we want to add the resources, it will allow us to apply the resource, but we don't need to do that in this video. I may create another video for the full process of applying resources, correlation, and register in another video. But for video for cost planning purpose, we don't have to do that. And then now we come back to the cost and click the risk and run risk analysis. And then we will analyze for 10,000 iterations. Let me discuss a little bit about this type of risk analysis. The software will apply the Monte Carlo simulation. That means they will change the maximum and minimum cost from, for example, for soil excavation, they will change from 38 to 63, and not only these items, they will randomly change the cost and do combination to identify the probability of B from B0 to B100 that I have discussed earlier. And in here, if we click to analyze, the software will ask us, please say the blend before running risk analysis. Just click OK. And in here, if we click hit to step, it will run step by step. If we click to go, it will do much more faster, and it will hit to complete, it will do complete within some seconds. Yeah, so first I will click to step so we can see step. If you notice to the soil excavation, the mean fixed cost is from 38 to 63. It doesn't change, but it changes. Deterministic cost will change with the range from 38 to 63. You can see 47 fall within this range. Yeah, they do many times for many items. And if we do go, it will do faster. The asset go complete, we just OK go. We can see the projects has been running, and if we click complete, it will complete right now in some seconds. And then the distribution graph will appear. You can see here the this is the bell, the bell curve, and in the right column is our confidence level from B0 to B100, and deterministic, that means our base estimate. And here, if you remember our B50, that means the project 50%, the project will be completed within this cost is 97. I will come back to the Excel file. Here 99. If we calculate manually, is 99, but if we use software, is 97. And then and 90, we can refer to this paragraph. That is 114. We will come back to the Excel file. Is 137. There is a little bit differences. Then we can close this, but this graph. Actually, we can also have some further analyzers, but because we don't use the schedule, so it is not necessary. We will click close, and we also bring out the view, click close, and in the report we can summary risk report and build report. Hang on for a moment, it will have us to build report here. And tornado graph I will discuss in another video, because this video will focus on the cost planning, the contingency for cost planning. So in this video, I have discussed the importance of the contingency quantification for cost planning. Thank you for watching and see you in the next video.